And good morning, friends, and welcome to this first lecture, The Amazing Space, India's Space Science Exploration. And thank you all for having joined today's program on space science and technology. At the outset, let me tell you that this lecture is meant for offering a holistic perspective of space science and technology to the beginners and to generate a general awareness about the contribution of India in this domain. So at this juncture, I wish to share with you that during my introductions with the student community, which includes students from schools, colleges, and universities, and even the senior students like who have completed their PhDs, I have asked them, what do they mean by space? So every time I have asked this question, I have received different kinds of perspective, and I cannot say any one of them was wrong. Space is indeed enigmatic. See, when I'm speaking with you, at some parts of the universe, several stars are taking birth, and while several of the stars are coming to the end of their lives, and several celestial objects are merging, some celestial bodies are exploding, spreading the particles and waves to every corner of the universe as remnants of those events. In every second, numerous neutrinos are piercing our bodies, which are originated somewhere in the vastness of space due to some physical process taking place there, yet we exist and evolve. We exist as a wave in this endless ocean, and the humble manifestation of this entirety, this macrocosm, is what we call space. And space is an ever dynamic process, I should say, because in Sanskrit, if you take the word Jagat, it means etymologically that whatever moves, always in motion, is this Jagat, the space. So the scientists from different backgrounds perceive space in their own ways, so they have different notions. If you ask an atmospheric scientist, he or she will give a certain kind of answer. If you ask a mechanical engineer, the person will say it is a challenging environment with harsh conditions. They will focus on designing the spacecraft and technologies that can withstand the space environment. If you ask a nuclear physicist, you will get some other perspective. You will see they are investigating space from the fundamental particles and interactions. So they explore the cosmic rays, particles from space that provide insights to the high energy processes occurring in the universe, and study phenomena like, say, nuclear fusion that powers the stars. Ask a theoretical physicist, it is a complete different notion which is going to come out. They will say it is an abstract mathematical concept, and they explore the nature of space-time, the gravitational forces, and the cosmological models to understand the universe structure, its expansion, and other concepts, enigmatic concepts like dark matter and black hole. And the term space has got different notions as well in our daily lives in society, which you can see from the right side of my slide. Now, if you ask this question to the space scientists, yet they differ in their opinion about the realm of space. Where does the space start? So that all depends on the physical phenomena they are interested to study. So for practical reasons, it was necessary to demarcate between sky and space. More so, it was in the beginning of the 20th century, you know, that the Wright brothers demonstrated the aeroplane, the flight of human beings. So the difference between sky and space was a big question. And if you ask a child, what do you mean by sky? Sky, he will say, okay, if I stand in the middle of a field, and if I look up, I see a blue canopy over me, and to me that is sky. Perfect. What is space? A child will take a black pastel and draw black colored space. So you ask this question, why sky is blue and what is that dark part? It is space. So as you know, that sky is blue because you have enough number of atoms, molecules, and they cause the scattering of light. So those who know the types of scattering immediately will tell there is a phenomenon called Rayleigh scattering. And because of the shorter wavelength, the blue light, which is also seen by the human eye, that gets prominence in the process of scattering, and the sky appears blue. And space is dark because it is, I will not say nothingness, the number of such entities which can interact with the light is very less. So there is no effective scattering which can excite the retina of your eye. So it is dark. So this definition of sky and space is based on optics. There was yet another definition of, not definition, the demarcation between sky and space, which was with respect to aerodynamics. So you know that the principle of flying of an aircraft. So why the aircraft does not fall? Because it does not fall because of a force called lift, which is possible because of the interaction of the gas molecules in the atmosphere with the structure of the aeroplane. And this is necessary to keep the plane floating. And that was the beginning of the subject of aerodynamics. And at this juncture in the early 20th century, the Hungarian-American aerospace engineer, his name was von Karman. He conducted some groundbreaking research in the field of aerodynamics and the physics of flight. And he recognized that as an aircraft ascends into the atmosphere, the air density gradually decreases until it becomes indistinguishable from the vacuum of space. So von Karman proposed that the boundary between the sky and space should be defined by an altitude at which the air is too thin to support a conventional aerodynamic flight. So his focus was on aerodynamics, so he has seen space and sky in that perspective. And von Karman came up with the concept of an imaginary line, which we call today the Karman line. The Karman line, which I have shown by the dotted line in this slide, is an imaginary boundary which is at an altitude of 100 kilometers above the mean sea level. And at this altitude, the atmosphere is thinner by 7 orders of magnitude as compared with the density of atmosphere near the mean sea level. And the speed required for an aircraft to generate enough lift to maintain flight becomes impractical. Instead, spacecraft and satellites must rely on different propulsion methods to maneuver and maintain the orbit. Now, this Karman line therefore serves the demarcation between aeronautics and astronautics. So below the Karman line boundary, aeronautics deals with the study on the engineering of aircraft and that operate within the Earth's atmosphere, including the planes, helicopters, and drones. Above that line, astronautics focuses on the spacecraft, satellites, and exploration beyond the Earth's atmosphere. But at this juncture, I wanted to tell you this Karman line is a concept, but it is not very sacrosanct because scientists have understood that there are several interesting facets to observe and understand well below and above the Karman line. So around the Earth, the two most important entities are, one is the neutral atmosphere and the ion atmosphere, which we call the ionosphere. So all of you know about the neutral atmosphere, and we know that it is a nitrogen dominated environment. And then as we go upwards in the altitude, there are temperature variations at different altitudes because of several reasons of chemistry, several dynamics that happen between the light which is coming from the sun and the chemical reactions. So chemical compositions at each level vary and solar radiation varies, and which gives rise to a wavy pattern of the temperature profile at different altitudes. And that was the basis of demarcating different layers of the atmosphere like troposphere, stratosphere, so on and so forth. And one more thing, you know, that it is all exposed to the solar radiation, and the high energy part of the solar radiation, especially the ultraviolet and the X-ray radiation, what do? They interact with the gas atoms and molecules of the atmosphere, especially in the upper atmosphere. And as these high energy photons interact with a given neutral atom, what happens? The outermost electron is stripped out, leaving the neutral atom as ion. And that's how the ionosphere is formed. And ionosphere also has got different levels. Without going to the much of the details, I must tell you that different layers of the maximization of the ion density happens at different altitudes, and they vary in day and night. In the right side of my slide, you're able to see what happens in the day and what happens in the night. And in both the cases, in the left hand side, when I've shown the Earth's atmosphere, and the right hand side, I've shown the ionosphere, I have marked the Karman line in red color. And I'm trying to show you both above and below the Karman line, a lot of interesting facets are there. So ionosphere extends typically from 60 kilometers to thousands of kilometers above the Earth's surface. and plays a crucial role in various atmospheric and communication technology. And so far, so good. Earth, the neutral atmosphere, and the ionosphere. But as I mentioned in the beginning of my lecture, that things have to move, things are dynamic. So here, dramatization happens, and in the drama, took entry one entity, which is the Earth's magnetic field. And from the basic understanding of physics, you know, a charged particle is disturbed by electric field and magnetic field. And also, you know, a few things like a moving charged particle gives rise to a magnetic field. Now, just imagine the situation. You have a magnet called the Earth. You know that Earth can be approximated by a bar magnet. And you have the ions, the ionosphere, and there will be interactions between the ions and the magnet. So before entering to that discussion, we will just glance through the concept of the origin of the Earth's magnetic field. So even it is often called geomagnetism, and which is a result of something called geodynamo. You know what is a dynamo? That is a device that converts a mechanical energy to electrical energy. In similar lines, a geodynamo is a process and which is happening in the deep inside the core of the Earth. The Earth's core consists of two main parts. One is the solid inner core and the liquid outer core. The liquid outer core is made primarily of the molten iron and nickel. The geodynamo works because of the movement of this liquid in the outer core. And this movement is driven by the immense heat within the Earth's interior. As this liquid flows, it undergoes a phenomena called convection, which is similar to, you know, when water boils in the pot, the hot water rises and the colder part of the water is sinking. Same phenomena. This convection, which is happening, this creates some circulating patterns of the molten iron in the outer core of the Earth, and these circulating currents, combined with another motion, that is the rotation of the Earth, produce the phenomena which we call a geodynamo. And this geodynamo generates an electric current, which in turn generates a magnetic field that surrounds the planet Earth. And this magnetic field extends into space and is often referred to as the geomagnetic field. Now, one thing you have to remember that geomagnetic field, if you consider this as a bar magnet, you may expect the magnetic field to be a perfect sphere. But that doesn't happen because of various reasons. One main reason is when you have sun in one side of the Earth and sun is also having a magnetic field, so there is a power play between two magnetic fields. One side sun's magnetic field, other side Earth's magnetic field. So there is a pushing effect, interaction effect. So usually towards the sunward side of the Earth, the magnetic field is pushed towards the Earth. Okay, and in the anti-sun side, the magnetic field is elongated. So this is a peculiar shape of the Earth's magnetic field. And this field serves as a protective shield to us, and it traps the charged particles coming from the sun, which is referred to as the solar wind. And it plays a crucial role in Earth's retaining the Earth's atmosphere and its inhabitants, including us, from the harmful effects of those charged particles. And additionally, this geomagnetic field is responsible for creating phenomena, beautiful phenomena like northern and southern lights, aurora borealis and aurora australis, and which are mesmerizing displays of colorful dances in the sky near the high latitudes, especially in the polar regions. And you also will appreciate that this bar magnet, the hypothetical bar magnet, the magnetic pole and the geographical pole are not exactly the same. And there is an 11-degree offset between these two. So that also had some implication in the history of our space program. And it is interesting. And the geomagnetic field plays a significant role in shaping the behavior of the ionosphere as a tool, and especially the region under the geomagnetic equator. And one fascinating phenomena influenced by this geomagnetic field is the equatorial electrojet. So if you're not familiar, if you do a search in the internet or go to the ionospheric books, you'll be able to find about this peculiar phenomena. And this equatorial electrojet is refers to a very narrow and eastward flowing current in the ionosphere, which happens in the magnetic equator region. And this current is caused by the interaction between the geomagnetic field and the ionized particles in the ionosphere. And the geomagnetic field guides the flow of the equatorial electrojet in the ionosphere, which is the strongest during daytime and not so for obvious reasons when it is night. And it has got many practical implications, like it can affect even the accuracy of navigation systems that rely on the radio waves that are supposed to pass through the ionosphere. Now, in 1960s, the study of upper atmosphere and the ionosphere near the geomagnetic equator emerged as a key area of interest for the Indian scientists. Recognizing the importance of this unique region, the Tumba Equatorial Rocket Launching Station, which we call TIRLS, was established in Tumba. It happened in 1962, and it is located under geomagnetic equator, and TIRLS thus provided an ideal launch site for rockets to explore the upper atmosphere and the ionosphere. And it soon became a hub for conducting experiments and launching sounding rockets to gather valuable data about these regions. And subsequently, Indian Space Research Organization, ISRO, was founded in 1969 with the objective of developing space technologies and harness space for the country's development. And since its inception, ISRO has undertaken numerous activities, including space science missions that have expanded our knowledge of the universe and pushed the boundaries of space science and technology. And in this course of lecture, I shall discuss a glimpse of the space exploration program of our country. Now, having discussed about Earth, let us turn our attention to the sun. The sun is a star that powers our solar system. It is the source of energy of everything, and it has a process of fusion which powers itself, and where what happens, the 4 hydrogen atoms combine to form helium, and there is a mass defect which is converted to E is equal to mc squared, that is converted to enormous amount of energy in the process. And this energy, what it does, it ionizes the gases and sustains the state of ionization and makes sun a giant ball of plasma. So what is plasma? It is a combination of positive and negative charge particles in a combined form, which is called the plasma. Total charge could be almost zero because positive and negative both are there. And it is also a dynamic process which is happening. And due to the dynamics of the plasma, the sun also processes a magnetic field. You have to remember, a charge particle in motion causes a magnetic field. Same thing is applicable to sun also, but it happens at a much larger scale. And the study of sun's magnetic field and its interaction with the surrounding space is known as magnetohydrodynamics. We often call it MHD. And MHD combines the principles of magnetism and fluid dynamics to understand how magnetic fields influence the behavior of the plasma in sun. And the generation of the solar magnetic field is also a very complex process. See, you can imagine sun, and you can imagine that sun's magnetic field is coming out. But you have to remember, sun is also rotating, and it is rotates in such a way that the middle part of the sun, that is the lower latitude of the sun, it is faster compared to the higher latitude. So there is a differential motion along different latitudes of the sun. So if you can imagine the magnetic lines as rubber band, and due to the faster motion near the belly of the sun, it is slung at a very faster rate, and it is spreading across the ecliptic line. And what will happen if you see from the top of the ecliptic? Suppose we could go to the top towards the northern side of the ecliptic and looking down, you are going to visualize something which is shown in the right hand side of the slide. You are going to see some spiral magnetic lines are coming, and they're pervading the space of the solar system, and in between located the orbit of the Earth, orbit of the Mars, Jupiter, and all the other planets. And this spiral is called Parker spiral, after the scientists who have discovered this facet of the magnetic field of the sun. And now we have got 2 giant magnets in space, the sun and the Earth, and which is separated by a physical distance of around 150 million kilometers. And you are aware what happens when you bring 2 magnets in close vicinity. Like poles attract and the opposite poles repel each other. And if you do not allow the magnets to move, say you keep them fixed in space, and the space between them undergo an interesting change. And you are aware that from an isolated magnet, there are some invisible magnetic lines of force that come out. Okay, and these magnetic lines of force are the lines, along which, if you put any tiny compass, the tiny compass's needle tries to align itself. Now you can perform an experiment. So what you can do is, if you can have a bar magnet like this. I don't have a bar magnet with me. A bar magnet like this. If you can fix its space, and if you have a tiny compass like this, you see the magnetic needle is going to be aligned with the bigger magnet, and then with a pencil you mark the north and south. And wherever you have marked the north, you put these compasses south there, again mark north and south, and continue the process. And as a process, you're going to get something like this. So these are called magnetic lines or forces, which originate from the North Pole and go to the South Pole. And this is a fantastic pattern. You can play with this game. Now you have got two such things, two bar magnets fixed in space, separated by a distance. And the magnetic lines of force form, the two bar magnets would attract or merge with each other if they are of the opposite direction. And the lines would repel each other if they are in the same direction. And I'm sure if you are good at making animations, you can make attractive and mesmerizing computer screensavers out of this concept. This fantastic dynamics, the merger of the magnetic field lines and repulsion, lot of dancing happens there. This process is called the magnetic reconnection phenomena. It is all about magnetism and the reconnection, which refers to the insensate dynamics of the making and breaking of the process of hand-holding between the magnetic field lines. So it is not a connection, not only a connection, but also a game of disconnection and reconnection. And that's why we say reconnection. You know from the basic physics that if you put some charged particle in a magnetic field, they follow the magnetic field lines in helical paths, Lorentz force. And as they move, they create its own magnetic field. Okay, so the charged particles, as they move, creates this magnetic field is statement. And the statement, charged particles follow the magnetic field is another statement. I leave to you to decide which one is the cause and which one is the effect. It depends mostly on the context. For me, a safer statement would be a charged particle in motion has associated with it a magnetic field which guides the former's trajectory. Sometimes we physicists get away with such jargons when we do not wish to enter into the complicated discussions of cause-effect relationships. And now let us make this scenario more interesting. Let us assume that out of the two magnets, one is a ball of plasma which displays intermediate instability. So this magnet is sometime oozing out something. They are unstable and it cannot hold back this entire amount of plasma to itself. Some amount of it is giving away to space. So you guessed it right. I'm speaking about the sun, and it is the one of the magnets which is a plasma and which is unstable and which is constantly emitting charged particles, which is called solar wind. Solar wind, is rich in the ionized hydrogen and helium and some small proportion of the heavier ions, which pass through the interplanetary space along the magnetic field lines in helical trajectories, while the emission of the solar wind is a continuous process that forms a background of the charged particle emission from the sun. There are some sporadic emissions due to this instability, and the process of magnetic reconnection conspire to provide the instability of the plasma a path of eruption, and after the eruption, propagation in the interplanetary space. And these processes connect the sun and the earth with the photons, particles, and associated magnetic fields from the sun. To remember it easily, the photon emissions in bursts are referred to as solar flares, and they are pretty rich in the high energy photons like X-ray photons. And the charged particle emissions are referred to as coronal mass ejections or CMEs. And the effect of the magnetic field that are associated with the charged particle emissions is referred to as geomagnetic storms. And once the geomagnetic storms occur, the magnetic field from the sun pushes away the Earth's magnetic field toward the Earth. So what happens? The solar magnetic field overpowers sometimes the geomagnetic field, which helps the former to inject some of the solar origin charged particles to the close vicinity of the Earth, and we refer this condition to as space weather. We often use the term weather. So weather basically is a condition of the state of space which is within the Earth's atmosphere, within the Earth's magnetic field. Temperature, pressure, humidity, all define weather. Okay, but as you are going out of this protection of Earth's atmosphere and the magnetic field, you are exposed to the deadly reality, which is the weather of the space, and it is in our solar system. It is governed by the mood of the sun. Whether the sun is going to erupt some photons or some particles associated magnetic fields, that all depends on the mood, and sun is very moody. The mood of the sun is having a cycle. Sun sometimes is very angry, not sometimes is not so angry, again angry, not so angry. It follows an approximately 11-year cycle. We call it a 11-year solar cycle. There are shorter period cycles also, but the 11-year cycle is very prominent. And we are in 2024-25. This time we are going to enter a solar maximum. That sun is now getting angry. Okay, so lots of these events are going to happen. So this is called what is called the space weather. Now, having discussed this, Earth and the near Earth space, let us turn our attention to the solar system. The solar system, as we know, it began the journey about 4.8 or 4.9 billion years ago from a giant cloud of gas and dust, which we used to call the solar nebula. And as the cloud collapsed under its own gravity, it formed a spinning disk. And this spinning disk is today what we call as ecliptic plane. And in the center, the sun was there, and the remaining of the material in the disk began to coalesce or clump together under their own gravitational influence. And this gave rise to planets and other objects in the solar system. And very well, you know, who are the members of the solar system. There are planets, there are natural satellites or moons, there are dwarf planets. So what are the dwarf planets? They are planets, but similar to the planets, but they have not fully cleared their orbits of other debris. Means the trajectory through which they move, or the orbit through which they move, they are not the only leaders. Comparable to their size, there are some other materials also they move along with them. So in astronomy jargon, we say they have not cleared their orbits of other objects. So they are dwarf planets. So one example is Pluto. And we have got comets, which are composed of dust, rock, and frozen gases. Icy bodies there. We called comets are dirty water ice. We have asteroids, which are rocky remnants of the early solar system. We have meteors, meteoroids, and meteorites. They sound similar, don't they? So a meteoroid is a small object, typically a fragment of an asteroid or a comet, that orbits around the sun. And when a meteoroid enters the Earth's atmosphere, and then what happens? They burn up, right? And we call them shooting star, and they have a name in space science. They're called meteors. And if any part of the meteorite survives and lands on the Earth, it becomes a meteorite. So next time you will not make a mistake in differentiating them: meteors, meteorites, and meteorites. And then we have Kuiper belts. It is a region of the solar system beyond the Neptune's orbit, and it is a home to numerous icy bodies, including, there's some short period comets are also coming from them. And we are having Oort's clouds, again a region located far beyond the Kuiper belt. It is thought to contain the billions of icy bodies and is considered the origin of the long period comets. Some of the comets which are long period, they are thought of having originated from that region. Now, at this juncture, I want to tell you that this Pluto, why it is no longer a planet? Because when we were school children, we have learned 9 planets, and we were supposed to memorize the names of the 9 planets. All of a sudden, in 2006, something happened. Many of you know there is something called International Astronomical Union, and they meet periodically. In their 2006 meeting, according to the International Astronomical Union, it proposed a definition that planet. It has a definition of planet. A planet must meet 3 conditions. Number 1, it must orbit the sun. No problem. Be spherical in shape due to its own gravity. No problem. Third condition, it should clear its orbit of other gravitationally significant debris. Means if you are a big object, similar to your bigness should not be there in your path. You should be the one king in your kingdom. That was not obeyed by Pluto. And there was another object called Charon, and that's why Pluto became a dwarf planet. And exploring the solar system is very important because it allows you to gain insights into the formation and dynamics of the celestial objects, and especially achieving a good amount of understanding of our solar system facilitates conjecturing about the other solar system and the planets therein, which we called the exoplanets. And to go to the bigger and bigger scale, where is our solar system located? It is situated in the Milky Way galaxy. And the Milky Way is estimated to have been around 1 lakh, more than 1 lakh light years in diameter, and contains billions of stars and along with various other celestial objects. And our solar system resides in a spiral arm of the Milky Way called the Orion arm or local sparks. Specifically, we are located around 26,000 light years away from the galactic center. And this places us in a relatively calm region. And this could be one of the reasons that why Earth or our solar system could host life. And the Milky Way is just one of the many galaxies, and many such galaxies form a supercluster. Like the Virgo supercluster is the home to our Milky Way, and our Virgo supercluster is one of the clusters. And in this picture which I am showing you what is called a schematic of an observable universe. And in the middle of the observable universe, as a point, I have represented the Virgo supercluster. You just imagine the point is basically a supercluster, and it gives lot of place to lot of galaxies. One of these galaxies is us, and one is this. In the galaxy, we are having a solar system. And there is a debate about the observable universe size. One thought is it is 93 billion light years in diameter. That number has come from the age of the universe. And if the age of the universe itself is debatable, then observable universe size is also debatable. Observable basically means sitting on Earth with all the technologies which you have, how much you can observe. It basically is limited by the speed of light. Okay, that limits the size of the observable universe. So thus this space research and exploration have both scientific and philosophical motivations. Scientifically, they allow us to expand our knowledge, understand the universe origin, evolution, our local space, and develop technologies to understand it towards a better future. And philosophically, it inspires curiosity, provide a broader perspective of our place in the cosmos, and foster a sense of wonder and in exploration that defines the very human spirit. Now, having discussed about space, the next question is how to study space, the techniques to study space. So if you ask me what are the techniques, I can give you quickly some answers. One is theoretical modeling, which is basically a fundamental technique for developing mathematical frameworks or mathematical models that describe the physical phenomena. It is based on the understanding of physics. And there is another thing called computer simulation. Computer simulation is a tool where scientists are enabled to recreate complex space environments and phenomena in a virtual setting. Likewise, you're having another way to do laboratory simulation. The laboratory simulation, it involves creating controlled experiments on Earth to replicate specific conditions in space. One such example you can directly cite, say the question of how life originated on Earth. So you just remember in your biology classes, you might have studied how a jar was taken and the basic ingredients which were known to have been possible during the early days of the universe. They were created, and electric spark was passed, and how amino acids were observed. So this is a typical example of laboratory simulation. There are many such people do. And another thing is the ground-based observation. If you're having a telescope looking at the sky, yes, you're doing a ground-based observation. So that is another way to observe the space. Yet another way is the big data analytics. That is, you have lot of data from the observations, and with some techniques of artificial intelligence and machine learning, you basically try to find out some pattern. And from the pattern, you try to understand nature. So that is one kind of, for that you are not going to the physics, but you are doing an big data analytics kind of process. But at last, I would like to mention you about a space-based observation, which takes research beyond the Earth's atmosphere. The space telescopes which are in space provide unobstructed views of the universe, free from atmospheric interference, and they enable observations across the different wavelengths, revealing detailed information about distant galaxies, exoplanets, and several celestial processes. Now, although I have told you all these techniques, theoretical modeling, sample analysis, ground-based observation, space-based, in this slide, I have shown things in isolation. So you might think that they are isolated process. Let me tell you they're not. And this is a part of a process. And the process is called space research. And there are three major components: modeling, simulation, observation. I have described what is meant by modeling. I have told what is simulation. I have also told what is observation. So you can start at any point of time. Let us start at modeling. You can do a physics-based modeling or big data analytics-based modeling. And this modeling you use to do simulation. You simulate in a computer in the virtual environment, or you simulate in a laboratory environment in a controlled environment. And this simulation you fit to the observation which you are making to add meaning to it. In the language of space sciences and astronomy, we use a very difficult word. The difficult word is we constrained the observation, the models with the observation. Okay, so this thing happens when your wisdom which you have got by modeling goes into simulation, and simulation goes into observation. Learning from observation goes to modeling, so on and so forth. Observation is also not limited to space. It is also ground-based observation. It is also observation of the samples, the kind of sample which you bring from moon to earth. We call the sample return missions. Also the samples which are meteor samples, due to some conspiracy in nature, some of them land to earth. They might have come from elsewhere. So they are made available to you. You do laboratory analysis. In India also, they are in different labs. These meteor samples are analyzed, and the Physical Research Laboratory, PRL, does a fantastic work in this domain. So this is a process, entire process. It's called space research, and exploration is a part of this whole thing. Now, when we say observe something in space, what we observe is you can observe a celestial body or matter. You can observe some processes in the celestial bodies or matter. You can observe a star, observe a planet, you can observe a natural satellite, you can observe even the particles or the dust, interplanetary dust. Okay, space has dust. And when I say planets or stars or any body, I mean that you are studying its interior, its structure, its surface, its atmosphere, its interaction with the sun, so on and so forth. And you can also study the processes like merger of the different celestial bodies, burst of photons, expansion of celestial objects. You can go on naming. Now, who carry this information to you? You will say it is electromagnetic radiation, the photons. Not necessarily only the electromagnetic radiations. Let me tell you, there are other messengers which bring this information to you. One kind of messenger is the field, electric field and magnetic field. Another kind of messenger is neutrinos, which are the fundamental particles, and they can penetrate almost everything. And they are anyway very good messengers because there is no obstruction. Then you have got the cosmic rays. They also carry information. You also have gravitational waves. Now, what are the gravitational waves? Those who have studied the domain of electromagnetics, if we have a charged particle, it gives rise to electric field when it is at rest. When you make the charged particle move, it gives rise to a magnetic field. And when the charged particle accelerates, it gives rise to electromagnetic field. Similarly, when a mass accelerates, it gives rise to a gravitational wave. So it is just a wave in the space-time continuum, which is reaching you at every moment, which represents some phenomena which has happened at some part of the universe, and you are basically immersed into these kinds of waves. One such wave is gravitational wave. Another kind of wave is the cosmic microwave background radiation. So I will not go to that details. Now, out of these different kinds of observations, let me tell the merits of space-based observations. Space-based observations, when you are observing something from the space, you are away from the atmospheric haze. When you are beyond the atmosphere, some wavelengths of the light which could have otherwise been absorbed, those are not happening. Atmospheric scattering is not happening. Ionosphere is not coming into the way, which could have disturbed the radio waves which you are using as your messenger. But that's not enough. Sometimes you would like to study beyond, not only beyond the atmosphere, beyond the magnetosphere also, especially when you are trying to study the charged particles. You don't want to be you don't want your observation to be shielded, so you have to be beyond the magnetosphere of the earth. And if you have some still special requirements regarding visibility, at every time I want to see the sun, no obstacles, so you have to choose some special vantage points or strategically located points, which are called the Lagrangian points, L1, L2, L3, L4, L5, for any two bodies which are gravitationally bound. You know that they rotate around their common center of mass, and there are 5 points around them which are gravitationally, gravitational equilibrium points, not necessarily all are stable or unstable. Lagrangian point 1 is something which falls between the two bodies where their gravitational forces get cancelled out. So which is an unstable equilibrium, small here and there, and it starts going to one of the celestial bodies. So these are some merits of the space-based observations. So having discussed this, let me tell you what are the kinds of platforms. You have different kinds of platforms depending on the use. You have scientific balloons, but it doesn't go beyond 40 kilometers. 50 also is a very exotic thing. I will limit it to 40. And you have sounding rockets, which goes and falls. It doesn't allow you much of an observation time, but it can give you a low-cost access to space, typically from 70, 80 kilometers from the mean sea level to a few hundreds of kilometers above that. Then you have satellites. If you have to make a prolonged observation for a few months or years, you have satellites. And you have, platforms like landers, wherever you find that, satellite observations are not enough. You're getting global coverage, but you want to do the ground truth observation. So you have to send a lander. And you also are not satisfied with that. You want to rove around to see within the close vicinity whether there is some differences from space to space. We call it a heterogeneity, spatial heterogeneity. For that, you need a rover. Right? There is another kind of mission wherein you neither send a satellite nor send a lander. You have a flyby mission. That is, you are going elsewhere. In between, you pass near a celestial body and do some observations. So advantage is that you get some extra information. Disadvantage is that you get a limited time of observation. Sometimes you have space observatories, like sit in one Lagrangian point and you see that continue seeing sun, or you see at some other Lagrangian point where from you see both sun and earth as a third party you see. So these are platforms and different vantage points for the space observations. Now, having said a lot of things, you might ask this question: how is a space mission planned? Chandrayaan-3 is on the way. We have launched Chandrayaan-2, Mars orbiter mission, Chandrayaan-1, AstroSat. It starts from a step. The step is, you will start from a fundamental question. And the fundamental question will sound more like a philosophy than a scientific statement. Often it sounds very simple, and it may be difficult to understand the context of the question. That is, whether it is a poetic statement or a scientific statement. An example of such a fundamental question is, how is the cosmic journey of a solar system? Step 2, you have to decompose this fundamental or poetic question to a set of certain semi-fundamental questions. The semi-fundamental questions are, more specific. Those specific questions sound more scientific than philosophical. As a continuation of the example which I have cited of the fundamental question, you can define a set of specific questions which must sound like, how did the solar system originate? Now you're not talking about cosmos, you're telling about solar system. How did the solar system evolve? How did the planets evolve so differently? You are not being specific. You are telling planets, you are indicating that they have evolved differently. Can the knowledge about the solar system be extended to other solar system? Can we extrapolate? These are certain semi-fundamental questions. And often answering these semi-fundamental questions may necessitate multiple space missions to study multiple celestial bodies from multiple vantage points. For example, if you're interested to study the chemistry of the early solar system, you may choose to study the permanently shadowed regions of the moon, which are believed to have been the repositories of the information regarding the early solar system. And if you're interested to study the evolution of a planet that has lost its atmosphere due to some reason, you may choose to explore the Mars. The bottom line is that once you break down the fundamental question to the semi-fundamental questions, you also have to choose the apt target. Apt target means the apt celestial body who may be the best candidate to offer you clues to the celestial, those semi-fundamental celestial problems. Step 3, you have identified the celestial body, right? Step 3 is select the study domain. Once your target is identified, you start answering what exactly would you like to study about it. Do you wish to study its interior or surface or atmosphere or magnetic field or something else? Then comes the step 4. Step 4, you're going to more specifics, going to the parameter level. You parameterize, select the parameters. And once the domain is identified, the step is that make a list which parameters you want to study, and along with this list of the parameters, write the parameter ranges, the accuracies of the parameters to which you want to make the observation, resolution, which are necessary to make some meaningful scientific observation. Now at this step, where one selects the techniques, the instruments to make the observation, because not all parameters can be studied by all kinds of instruments. So basically in this step, you know what kind of instrument, whether some telescope or some magnetometer or something else you're going to study is defined in this step. Then step number 5, you decide about the platform to make these observations. Would you like to achieve a global coverage of the celestial body? Then you have to have an orbiter with a possible suitable geometry of the orbit. If you wish to perform a scientific analysis at a given location of the celestial body, you may choose a lander or a rover platform if it allows you. Once it is chosen, the next step is to arrive at the observation plan. So these include preparing a plan when to observe and the operational mode of the instrument to invoke and to store the data. There are some facets which I have named. This stage of planning also includes the aspect of visibility of the ground stations and the plan for the data download. So you're going to the specifics from the fundamentals. And if you take any example of any mission globally, you take our own mission Chandrayaan-3. It also has paved the similar way of the steps. You must have appreciated by now that a given space mission cannot provide the ultimate answer to a fundamental question. It is the collective effort of numerous scientists and engineers to plan several space missions that provide diverse perspective to several semi-fundamental questions, and arriving at the answer to the fundamental question requires putting together all the pieces of information like a jigsaw puzzle available from all the space missions, ground observations, simulations, modeling. And this is precisely why a holistic and philosophical view is necessary to become a space scientist. Now you have understood how a space mission is configured. Now, what is the basic components of a space mission? Major, there are 3 components. One is you should have a rocket to access the space. You should have a space segment, that is you have a spacecraft or space probe which is in space. That is one of the components. and you have a ground segment. Among the ground segment you have, what all the things you should have? You should have a mission control center from where you will be able to send commands. I have shown an arrow showing that a telecommand is being sent from the ground to the satellite. And from the satellite, you're having some information about certain parameters of the health, or satellite itself is sending you some signal, which we call the beacon. See, I am here, and hence it enables you to track the satellite. So, okay. So telemetry tracking, they happen from the mission control center. And another sort of ground station is, data reception center. So the data come from the spacecraft. So these are the major components of the space mission. It is not only the rocket or the satellite which does the job. And now let's come to this part of the journey, India's journey to the space. So India's space research program has undergone different phases. It started, I'm not telling ISRO, mandate, I'm telling India. So 1920s, the famous experiments of Professor Shishir Kumar Mitra on the radio sounding experiments of the ionosphere, that we consider as the first set of experiments where ionosphere was studied using radio waves. And this continued for a while, and 1940s, India witnessed the establishment of Tata Institute of Fundamental Research and the Physical Research Laboratory by Dr. Bhabha and Dr. Sarabhai, respectively. And in 1950s, Department of Atomic Energy was formed, and 1962, INCOSPAR, Indian Committee for Space Research, was set up under Department of Atomic Energy. And 1969, ISRO was founded, and it continued. Space Commission and Department of Space came into being in 1972. ISRO came under Department of Space, and after that, there have been different phases of ISRO. All this information you're going to get in the ISRO website, so I'm not going to dwell on it. What I wanted to tell you is like this. One significant, all these milestones which we have crossed, we have started our observations from the balloon-borne experiments from TIFR and sounding rocket experiments. And the first set of experiments in 1970s and 90s, 80s, they were on X-ray astronomy and aeronomy and solar physics. The first mission was Aryabhatta in 1979, and then we had SROS and Indian X-ray astronomy experiment for X-ray astronomy, and the journey continued. And you will appreciate one thing here. There was a time when we didn't have any dedicated science mission, and in the 2008 onwards, when it was the beginning of the planetary exploration of the country, we started having dedicated science missions. Previously, it was having a scientific instrument in some other operational satellite. So that started continuing, and we have paved a journey up to Chandrayaan-3. And that in future we are having Aditya L1 mission and other missions in line. Now, the whole gamut of the space exploration is divided into 4 verticals. Astronomy, astrophysics is one vertical. I need not explain what are those. Heliophysics and space weather studies is another domain. When I say heliophysics, it is the physics of the sun and the effects that sun causes to the other members of the solar system in terms of its particles it emits, its its photons it emits, the fields which are associated with the charged particles, the effect, the space weather, entire thing is heliophysics. Planetary exploration and upper atmospheric studies, which is called aeronomy. Now, all these verticals are interconnected. I cannot say they are isolated islands, and they are multidisciplinary. And I must tell you, there are many other verticals which are opening up: astrochemistry, astrobiology. So this slide gives the youngsters the indication. Presently, what do we have, and what are the openings for you? And I must say, modeling, simulation, and observation process goes on happening for this as well. All these verticals. And let me tell you about something about the space missions which we have flown. See, the Chandrayaan-1 mission has changed the perspective of the moon, I must say. I will justify why I am making such a bold statement. Before Chandrayaan-1, we used to believe that the moon is bone dry. Chandrayaan-1 made us understand that moon is not dry. It has got its repository of water, not as a liquid water, but as water ice on the surface, subsurface water, and also water vapor in the moon's exosphere, moon's tenuous atmosphere. Then it was a belief that moon is geologically dead. Geologically dead means, it is a jargon again. It means basically you don't have any internal energy left with the planet. When there is no internal energy left, there is no volcanism, there is no plate tectonics, there is no movement, right? It was believed that moon is so, but the mission Chandrayaan-1 has revealed it is not so. Then there was another belief, moon's regolith, the powdery surface, is such a substance which completely absorbs, all the solar wind particles, photons. Chandrayaan-1 said no. About 20% of the solar wind protons are reflected back. And this enabled us to do what, Earth, moon, doesn't have a global magnetic field, but moon has some small patches of magnetic field. If you could see magnetic field with your naked eyes, you could have seen some small igloos on the moon's surface. They are all mini magnetospheres. With these reflected neutral atoms which are coming out of the surface, scientists could map the location of the mini magnetospheres of the moon surface. And there are many such discoveries. It is not possible for me to tell in this limited time. Chandrayaan-2, it gave you the global distribution of the argon-40. This is a substance which is indicates some radiogenic activities which is happening in the interior of the moon, some radioactivity happening, wherein radioactive potassium-40 is converted to argon-40. And over the moon surface, for the first time, the Chandrayaan-2 mission's JS2 instrument has studied the distribution of argon-40 and how does it change with the day and night. We tell the diurnal variation, and which does a lot of indications about the dynamics of the moon's exosphere. And also we have got very good indication about the global map of the sodium, elements like sodium and other like manganese and other trace constituents, calcium. Calcium is not trace calcium, is quite significant, aluminum, and small craters and boulders using the very fine resolution of the OHRC instrument, which is the finest of the cameras presently available in the moon's orbit. That is from India, our country. Chandrayaan-2 mission is carried. Unambiguous detection of the lunar water ice from the IIRS instrument, which is in Chandrayaan-2. Revelation of subsurface craters using the synthetic aperture radar in Chandrayaan-2. And Chandrayaan-2 also has studied a lot of features about the sun. It has studied the microflares which is happening in the sun, which in turn is providing very good scientific clues about answering the coronal heating problem. So you can go on naming such missions. Mars Orbiter mission has got very good scientific outputs regarding the interaction of sun with the atmosphere of the moon, of the Mars, and how this ionization takes place and how the composition changes at the noon of Mars or at the evening of Mars. How does it change? And it also has discovered the highly energetic argon atoms from the Mars, which gave some clue about how the atmosphere of Mars could have escaped. So maybe in another 10 minutes, I have to stop my lecture. So I will try to give you a glimpse of the achievements of the Indian space missions. So after having said about these missions, I will tell you about AstroSat. It makes all of us proud. AstroSat was launched in 2015, as you know, and it has got lots of discoveries in its credit. Discovery of UV photons from the earliest galaxies, discovery of phase-resolved X-ray polarization in Crab pulsar, and X-ray polarization from several gamma ray bursts, and detection of the evolution of a gamma ray source stuck in a very long flaring state, exhibiting dozens of states of its activity. And it also contributed significantly towards solving a puzzle of a cosmic source. And the source was seen to have been bright in both infrared and UV. How could it be possible? Later on, it was found there was a hidden white dwarf. So it was just like it was giving a proxy. And AstroSat UVIT, there was an instrument, ultraviolet imaging telescope. It has witnessed the live formation of dwarf galaxies by detecting massive, young star-forming complexes beyond the visible boundary of faraway dark galaxies. So basically, we have seen histories, and very soon we are going to send XPOSat mission, which is India's first dedicated scientific satellite for studying polarization measurements from X-ray emissions from the celestial bodies. So that will have its own importance when so far you have studied how does a celestial source blink. That is information with time. You have studied its spectrum, composition. Now you are going to study, apart from spectrum, apart from timing information, polarization information, which will give you some additional insight about the several processes which happen there. Now here, this slide, I would like to thank Dr. Dipankar Banerjee, who is the director of IIRS, fantastic center in Nainital. This is about the Aditya L1 mission, which is going to be India's solar observatory, which is going to study the sun in multiple wavelengths. Okay, I am not going to go to the details of this slide. Only thing, the take-home message I want you to carry is India's Aditya mission is a world-class mission which is going to sit at the first Sun-Earth Lagrangian point, going to have a continuous view of the sun, and it is going to study the solar corona in the visible part of the electromagnetic spectrum, going to study the UV part of the spectrum of the photosphere, and also there will be a lot of other observations in terms of the solar wind electrons and the solar wind ions and the magnetic field which is associated with the charged particles. And the mission is going to go soon. And at this juncture, I must tell you this lecture will remain incomplete if I don't tell you about our own Indian repository of the space science data. So you must visit this website, www.issdc.gov.in, Indian Space Science Data Center. Even if you go to the ISRO's website, www.isro.gov.in, there's a link. And in this link, you are going to get the data which you can download, register yourself, download free of cost and start using. Indian space science data is available for you, all of you. You can start using it. Is that all? No, that is not all. There are major ground-based observatories in astronomy as well as the solar physics in India. To name a few, I have given a list. I'm not going to list the names here. I must tell you all these space-based observations are complemented and supplemented by ground-based observation at different wavelengths of electromagnetic radiation, and some of them are using some other messenger for this observation. So coming to the conclusion, why start? No, at this juncture, I must tell you, start is to kindle you, to show you future directions. If you ask an astronomy person that what we should do in astronomy, he will tell you some open problems in astronomy. Ask the question to a planetary scientist, he will tell you some open problems in planetary. I will not pave that path. What I will tell you is how to logically think about any domain you choose. That's why I prepared this generic slide. First step is you do a literature survey, identify the open problems in the field. And for this purpose, often you need a guru here. Now, next is what are known till date and how do they possibly connect to the unknown? So open problems, how they're connected with the knowns today. And it is you have to introspect. Guru can take you up to a certain extent. Then you have to introspect. Introspection will be able to give you the second point. Then, after having chosen your open problems, can you conjecture the possible answer? Can you put up a hypothesis? Can you design an experiment to test the hypothesis? And don't ignore your gut feelings. See, Max Planck has not ignored his gut feelings, and that's why Planck's quantum hypothesis has been there. Schrodinger has not ignored his gut feelings. That's why the Schrodinger equation was there. So often there are certain self-originated, which does not come fundamental, at its own merit come. That is your gut feeling. And then you pave the path, theoretical modeling, simulation, plan for observation. And here you need to decide what are you good at. Ask yourself, theory, simulation, instrumentation, and whatever you want to do may need some technology. Technological gaps you have to find out. Realistic constraints you have to find, whether you want to collaborate, and what is needed is the system level thinking. Be realistic in your path, and then you can give birth to new scientific missions. And the space, the students who are attending this program, you must be asking this question: how my subject fits. If you're studying physics, let us say, it forms the foundation of the space exploration, providing the fundamental understanding of the laws of nature and the behavior of the matter, energy, and space. If you're studying chemistry, it plays a crucial role in analyzing the composition of the celestial bodies, understanding the chemical reactions in space, and developing materials for spacecraft and equipment. If you're a mathematics student, it has got a very essential role in modeling, simulation, orbital mechanics, flight dynamics, whatever we call, trajectory calculations, data analysis. Computer science, I need not say, everywhere it is. And associated with it, if you're doing artificial intelligence, very much needed, robotics very much needed for autonomous operations. Electronics communications is a vital role in designing and developing spacecraft instrumentation, communication system and satellite technology. Electrical engineering, mechanical engineering, I think I don't have to explain each and every how you find some role. Okay, everybody has some role in this journey. Now, what is important I want to tell you before I conclude, that is, space exploration requires a system level thinking approach that transcends the boundaries of individual subjects. Integration of knowledge from multiple disciplines is crucial to address the complex challenges of the space missions effectively. And the ability to understand and collaborate across various domains ensures a holistic approach and that fosters innovation and breakthroughs in space exploration. So you see the cartoon here. If you follow this cartoon, you will understand how many domains are discussed here. The domains which we have covered in the cartoon are optics, chemical engineering, structural engineering, thermal engineering also. And you may ask, what are the tips? How can I become a system engineer? I am studying physics. How can I become a system engineer? Now, let me tell you, there is no royal road to achieve system thinking. There are a few suggestions, however, for the students who can cultivate such a perspective. One is you may choose unconventional combination of subjects, and there is a risk. People don't take that risk. Unconventional combination of subjects often give you this perspective, and you have to engage in different projects, attend conferences and workshops, engage in space-related clubs and organizations. Nowadays, many universities, colleges, or even outside public domain people have these kinds of organizations. Seek mentorship. Listen to the people who have done this, who have burned their fingers. These are a few. Remember, developing a multidisciplinary system level view takes time and effort, and it requires an open mindset, curiosity, and willingness to explore one's primary domain of study. And one thing I must tell you here before I conclude, that is, Atmanirbharata, that is self-reliance, is not meaning that everything you have to do. Atmanirbharata has multiple aspects. One aspect is when you are collaborating with somebody, collaboration means give and take. In national level, even in international level, you have to give something and you have to take something. So you grow. Atmanirbharata means you are having to offer something. You are able to offer. You are not always a taker. That is one aspect of Atmanirbharata, self-reliance. Another part of Atmanirbharata is, suppose something is not made available to you, you will have your confidence to make it, find some way to make it, some frugal way. These two things, if you remember, you will understand the importance of collaboration, and collaboration makes you grow. You collaborate and you have a strong base below your feet. And that's why the START program. Precisely because of this reason, we want to create an awareness about the fields of space science and technology, introduce to the different facets of space science and technology, which is going to happen in the coming days, awareness about the cross-disciplinary nature of the space science and technology activities, promote system level thinking, and program will help you to understand how do different subjects fit to different aspects of space science and exploration towards a bigger goal to generate awareness about the Indian contributions, not that everything is happening outside. We are doing it and we collaborate. We also give. People are coming to us. People are recognizing. So give and take and grow. This is the thing. And how our space science exploration program, they fit in the global arena of exploratory endeavors. And this program is expected to sow the seed of preparing the future leaders who will take forward the country's exploration. To summarize, I have told you about space, what is space, different notions, near Earth space weather, and give step after step a bigger perspective of space and the universe. Then I told about the space research techniques, different exploration platforms. I also discussed about how missions are designed and what are the components of a mission, ground segment, space segment, rockets. And then told about India's contributions, missions, data center, relevance of the START program, and relevance of system level thought, and pan-India studies of the space science. I have to tell you about this particular slide. The left-hand side slide is a book. Go to Google, search COSPAR, OSPAR, COSPAR, plus this title of the book you are going to get a 400-page PDF that tells you about in India who are the academic institutions at the institutions who are doing some activity in space research. This will be very useful for the students. And the right hand side is a small booklet which will be made available to you shortly, which in very easy way tries to introduce to you the different facets of space exploration for the beginners. So with this, I thank everybody for your kind attention. I am